In these sections, we're going to exercise using the very simple example for how to determine the stress, and using this formula. The concept is determine the force and then determine the area where you like to calculate the stress. And so we move on to the So let's take a look at this example. And the first step is to calculate the stress. And using this example, we're going to study the stress at different locations. For example, in this bar, for example, in this pin, etc. Okay. But anyhow, the first step is to determine the stress. Determine the force. And we are in particular interested in the force in bar BC. We also interested in force in bar AB, and the struct is under the loading 30 kilonewton here. So to determine this one, we simply take the free body diagram. So let me take the free body diagram of this portion. Okay, and by taking the free body diagram, you can see here. Let me draw this struct here. So that is the struct system, and so here is where we take the cut from, and here is a loading 30 kilonewtons, and we wish to find the reaction. So here the reaction you can assume, for example, in these directions, and FAB, let me call that is this one, and in this you can assume the reactions is in that direction, FBC. Sometimes the people will ask me, say, let me draw the free body diagram here. Okay, this is the loading, and people ask me, can I assume the direction in this, or can I assume the direction in this way? Yes, you can. Either way, that is okay, but the key thing is once you assume your directions, keep everything consistent in the remaining calculations. Okay, this is important. As long as you keep everything consistent with your assumptions, if your calculation is correct, then your result should be the same as other people, for example, assuming in these directions. Okay, so let us starting from here and using this direction, and then from here we simply take the force equilibrium and say the force in x direction equal to 0, and then the force in y direction equal to 0. For example, here we assume the x direction horizontal, y is vertical. Okay, and if you do this one, then you can simply formulate two equations, and then very likely is you can using this under this arrangement, basically this is a given loading, this is the assumed direction, you can put into this one. Okay, so from this simple triangle, you can quickly determine FAB in magnitude equal to 40 and FBC in magnitude equal to 50. Okay, otherwise we simply perform the equilibrium equations. And let me erase unnecessary informations. Oops. Okay, so so for this example, if you want to using these equations, basically fx, this one will be the component FAB. Okay, so let's assume the point right-wise is positive, and then the other component is contributed by FBC. And if you take the FBC in the two directions, so this is FBC and multiply with the component is 4/5. So that is in x direction, but that is pointing leftward, so that is negative FBC, and 4/5. The negative because these components point leftward per our sign convention is negative. Okay, the x component, that's it, and everything Anything else? No. So that is equal to 0. Okay. For vertical directions, then again, this is 30. So that is 30. And say, let's assume the sign convention positive upward. So the 30 here is negative. And the other y component is from here. And that is FBC and multiply 3 over 5. Sign convention positive. Okay, the whole thing equal to 0. Okay, so either you take this graph or you take the two equations, and you should be able to find the FBC, FAB. Okay, so that is the things. Okay, so right now we have determined the magnitude FBC equal to 50, and in this direction AC in that direction. Okay, and now we take the further look at this one. And right now, let me change my color here. So let me take the free body diagram of these portions here. Okay. So at here, you can see at these cross sections, and that cross section basically is to here. Okay. So basically, that cross section is look like this. If you look at this carefully. So that is a section here, and that is a portion here, okay? And this is the same cross section, and that is the FBC on this cross section is pointing to that direction. So on this cross sections, the force is action reaction pointing in that direction. So that is showing here, okay? So the whole bar is in static equilibrium. So this one must be equal to that one. The direction is opposite. So from here you can see for this portion, it is under tension because that is a force and try to stretch this portion. So that is in tension. So very important when you first want to learn this stress analysis, not only determine the magnitude, but also directions. In addition to the direction here, this is a bar. Direction is always in the direction of where the bar oriented. Then the third one determine its attribute, the tension. Okay. Now we come to this portion BC here. Okay. So this portion we take the free body diagram is this one. So let me move to here. So that's the free body diagram here. The other free body diagram you can take is this portion. So that portion is something like this one here. Okay. So from this free body diagram, we realize the magnitude we determined is this, and that is 40. So to the same cross section, that is the action reaction concept. So that is a 40 here. Okay, and in these portions, and due to force equilibrium, so that is a 40 is this. So that is just showing here. So for this case, you determine the magnitude is 40. Direction is in the same fibers of the AB in this direction. And now, most important, you can see this pair basically try to compress this portion. So that is compression. Okay, so that is our first step using the free body diagram to analyze the reactions in the components. So now we come to our problem here. So right now we have determined the force, and now in this graph you can see that is a very detailed illustrations of each component. For example, let us take a look at a little more details. And this is the side view. This is a front view. Okay, so this is a top view. If you would be the person, you look into that direction. So that's a top view. And this is the bottom view. And so, for example, if you look at this tract from the bottom side upward, and you will see like this. Okay. At pin A. Okay, pin A is something like this. There's a one pin through, and then connecting to this bar by a C clamp here. And this is a pin B, and similar, well, kind of structure like this one. And this is the pin C. And so And also here you can see for each bar we are given detailed dimensions. For example, BC, that is the circular shaft, there's a circular shape and diameter 20. And for AB, that is rectangular cross section and height with 50. And from the bottom view, the width is 30. Okay, so here that we have a basic information, we can move on to determine the stress at different locations. The first exercise, we want to determine the stress in rod AB. So which means here I highlight here, we want to determine what is the stress in the rod AB here. So in rod AB, we simply take a cross section anywhere, sometimes here. Okay, so that means here is a free body, the cross section we pick. Okay, and inherited from 2 slides before, we know the magnitude of the stress in AB is 50, and we know it is in tension. So in tension basically has a tendency to stretch the material point. So we point this outward. That is meaning tension. Okay, now we have the magnitude, and again by our stress, and the formula is magnitude is force divided by the cross-sectional area where is interested. So now we need to determine what is the cross-sectional area for this cross-section, and this is a circular portion, so the area equal to pi times radius square. Okay, so this shaft has the diameter 20, so radius equal to 10, pi r square equal to area. So here we determine A. The magnitude F equal to here. Okay, so we have a magnitude. So we do the calculations, and then simply is this 50,000 Newton, and then we put into the unit here. So basically in calculation is 159 Newton millimeter square. And this one, if you remember, that equal to MPa. Okay, and so this is the magnitude. And when we fully categorize a stress, first one we need to determine is the magnitude. Okay, the second one give appropriate unit. The third one identify it is tension or compression. So the 1, 2, 3 portions altogether will uniquely categorize a stress. Okay, so keep this in mind. And then now we move on to say determine the stress at the flattened end. So basically it's here. Okay, so we want to determine the stress at the flattened end of the bar. Okay, so for this portion I highlighted the cross section, I pick it up, and let me draw the cross section of the flattened end. So that is something like this. Okay, and then here is a hole, and to allow for the pin to go through. Okay, and then that's something like this. So from here, in the portions of the shaft BC, that is the cross sections area we're going to calculate for determine the stress. Okay, and so in this way, this portion based upon the dimension here, this is the height is the whole dimension from here is 40, and then this pin occupy the area 25. So basically this portion, this width plus this width equal to this one, 14 minus 25 equal to 15. Okay, and then this width equal to 20. So A equal to 20 times 40 minus 25. So that is this one. We determine A. And again, the magnitude in throughout the shaft, the bar BC equal to 50. So again, the magnitude equal to 50 divided by area, we just found it 167. Okay, and again, the magnitude, unit, and attribute tension. Okay. The second one, we change our focus to the bar AB, which at the bottom here. Okay, I just highlight here. So the first one, we determine the stress in the bar BC. So let me just take the cut, and take a cut. That's a cross section here. So again, the stress equal to F divided by A. And earlier we have determined the stress, the force has magnitude equal to 40 kilonewton. So F equal to 40 times 10 to the 3 Newton. And what is the area of this? The area has a cross section equal to this. So area equal to 1500 millimeter square. Okay, so 15 millimeter square. So put everything together, this is a magnitude unit. Okay, 26.7 unit. And again, C means compression. Okay, C means compression. And again, if you remember in this back to a few slides before, this is a feature here. This is the cross section, and this is the free body diagram of the AB, and the magnitude is distribution is 40 kilonewtons and 40 kilonewtons in this way. You can see the pair of the force on the two ends of two other cross sections in AB that has a tendency to shorten this portion here. So basically, AB, anywhere in AB is under the same condition in compression. So here we put a C, a simple word for compression. And sometimes you can see people using negative to indicate compression. So basically here people take the very common sign convention, minus for compressive stress and positive for so positive for tension, negative for compressions. Okay, so this is a common sign convention here. Okay, and this portion, let's skip off this here. Okay, so basically this one is a very this paragraph is simply saying that based upon very rough engineering approximations in AB portions, okay, this portion is about here. Okay, on the very rough engineering approximations, because the majority of the force has been confined between the two pins. The two pins try to, in the way, try to compress this portion here. So it's kind of estimated in this portion, which means about this kind of the corner block here, that has no stress there. And that is this paragraph saying this one here. Okay, but this is on the very rough engineering approximation. It's not so critical. If you wouldn't get it, it's okay. So the next one, let us exercise the shear stress. Oh, by the way, in this example and in this example, you can see the force is normal to the cross-section we pick, and again the force is normal to the cross-section we pick. So basically here we calculate is about the normal stress. Okay, compared to the normal stress, and here is the shear stress. before we go to the detail, basically, if you remember, the shear stress is induced by a force that is parallel to the cross section. Okay, so that is the reason why here in this page we focus on the shear stress. And again, as long as you determine the magnitude and then you calculate the area, then you simply divide the magnitude of the force by the area. You're still able to determine the magnitude of the stress. And again, for this case, that stress is shear. So here we still take the same formula, you can see, but you need to identify this stress is shear stress. So here we're using tau as the symbol. And again, here we divide the force by the area, cross-sectional area. That is a very the average sense. So here in textbook in 331, this class we're using average. Okay. In reality, the distribution of the stress is not uniform throughout the cross section, but it's okay. At the beginning of the mechanical material, we simply take the average. So that's the procedures. Again, once you determine the magnitude, and then once you determine the cross-sectional area, you can determine the magnitude of the stress. And here in our textbook, they come up with a few terminologies called the single shear, double shear, and even triple shear, depends on the situations. And so in addition to knowing how to calculate the magnitude of the shear stress, in the following two slides, I also want to define the single shear and double shear. Okay, and basically for this graph is single shear. The single shear is this. We take this as an example into details. And for example, here we concerned about the distribution of the stress in the pin, saying whether the pin will be strong enough to be able to carry the force that's being transmitted through the top and bottom plate. If, for example, the pin is too weak, then very likely the force here, they're going to shear off the pin going to be distorted or even break into two pieces. So here our concern is about the stress, the shear stress in the pin. Okay, so here that's the reason why we take the free body diagram on the pin, so like this. Okay, so once we have a free body diagram, you can see now the force being transmitted to the pins is this. One, the force on the top plate A has been transmitted to here and to push the pin around here, so that is represented by this one, basically P in magnitude equal to F. The second one is the force F prime that's been transmitted through the plate B and to apply to the pin to here, around here. So that is here in magnitude P prime equal to F prime. Okay. And then furthermore, in static equilibrium, force F and F prime in magnitude must be equal and to maintain the static equilibrium. Okay. And now once we know the distribution of the force on the pin, now because we want to determine the magnitude of the stress in the pin's cross section, so we further pick a cross section, say we cut here, okay, and the cut can be at the middle or a little bit above the middle. That's okay as long as you pick a cut, okay, just like this one. So here you can see once you pick the cut, and then that is the free body diagram you pick here. So you basically transcribe all the information that the free body diagram, that is the force being here. So this is the reaction and existing in the cross section you just newly picked, and in magnitude that equal to F in direction opposite to F, because that's the concept of the action reaction, or That's the concept of the force equilibrium. So by this, you determine the magnitude of the force, and which equal to P. Okay, so P. And given the size of the pin, you should be able to determine the cross-section of the pin. So that's A here. Okay. And now why it's called a single shear? The single shear, that means this reaction force in magnitude equal to F. So again, the reactions in magnitude equal to F divided by 1. And just because this one, that is where the definition of the single from. So from here, you could imagine, or you can deduce, the double shear follow the same logic. The double shear would be, here would be 2. Okay. So again, the definition of the single is from here. So in deduction, we could say, okay, if here would be 2, then it could be double. So we see, would that be true? And we can look at one more example to demonstrate the double. Then we can see the double first, second. Okay, we're back to the slides. So this is the double shear, and again, this is the pin's conditions, and the pin under this situation, okay, we take the free body diagram on the pin, and then in the similar way, we try to study the force being distributed on the pin. So again, this force applies through B, and then basically that is the, so let me take, I think in this portion we take the free body diagram is this one. Okay, so that is come to here. So here the force being applied to here through plate A, that's around here applied to here. Okay, and then on the top and bottom we use the plate C and D for connection, and assuming they are equally symmetric, so we're assuming the reaction exists here, here will be similar. So here FC, FD, they will be in magnitude will be the same. And so that's a reaction here. So this one, and this one must be inside the equilibrium. So in this case, P in magnitude equal to this, and in equilibrium equal to F. So from here you can see P must be equal to F divided by 2. Okay, so once you have determined the reaction here, so let me ask you, what is the shear stress at this cross section? Again, you have determined the magnitude, which equal to P, and you can determine the cross sectional area A. Okay, so P divided by A, that is our original formula for calculated stress, and here F divided by 2. So here, this, because this is 2 here, we define this as double shear. Okay, and but anyhow, that is the calculation compared to the single shear we just been talked about before. So here is kind of comparison for you, single shear, double shear. I can tell you this definition, single and double shear, only appears in chapter 1. Okay, so only appear in chapter 1. And in my experience, the single shear, double shear definition is not that critical. As long as you know how to correctly determine the stress through appropriate free body diagrams and then calculation, that will be good enough. Okay, and again, single and double shear, this kind of the uncommon definitions only appear in chapter 1. Okay. So now we continue to our here. So we continue our discussion on the single shear stress, and then we can exercise how to calculate the stress. The stress, for example, here we exercise is to determine the stress in the pin C. Okay, and pin C is here, and you can see pin C basically is pulled by this bar. And again, if you remember, that bar has the magnitude 50 and in tensions. And so from here you can see we take the free body diagram on the pin appear here, and this 50 transmitted to the pin to here, and this is a reaction to get everything in static equilibrium, this one must have a magnitude equal to 50 in opposite direction. So here's 50, here's 50, and now we want to calculate the stress in the pin. So we take the free body diagram here, we cut it. So this is a cutted cross section here. So now to determine the stress, we determine the cross-sectional area here, and that area basically equal to pi r square of the pin, and the force magnitude in equilibrium equal to 50. So that's a 50 here. So magnitude divided by cross-sectional area 102. So this is the shear stress. Again, this is a magnitude unit. And here you may ask me, do we need to determine the direction? If you could, and just like you already labeled in your free body diagram drawing here, so from this correct labeling of the direction, you already done categorize the shear stress. Okay. So in average, the shear stress in this cross section will be pointing in that direction. So under this way, magnitude, unit, and attribute, which means, for example, here the stress for shear is direction. Three things together, you are already completed in categorizing the shear stress. Okay. Now we move on to the next example here. So again, so that's okay. So here, sorry, this is slides for the double shear, and just for your reference here. Okay, double 2. So we continue to determine the shear stress, and we already in the previous example we determined the stress at the pin C. Now we move our focus to determine what is the stress at the pin here. So that is the pin here. Okay, so that's a pin A. So pin A basically is being pulled by this bar. Okay, this bar is this one. And again, if you remember from the very early analysis, the reaction in this bar is 40. Okay, and that is compressed. Try to push. So we take the free body diagram of the whole pin here, and that is a 40 being transmitted to the pin like this. And on the top and the portion, that is the ankle, and we're assuming that ankle basically making the symmetric. So in magnitude, FB here equal to FB here. So 2 FBs in magnitude must be in force equilibrium. So the magnitude equal to 20 here. So that is, if you, this is 20, this is 20. Okay, so here if you take the free body diagram of this middle portion, 20, 20, is actually in equilibrium equal to 40. And on the other side, you may also take the free body diagram of this portion. Okay, so let me highlight here. So here that the dashed line is the cross-sectional you pick. So earlier we have determined this is 20 kilonewton. So by action reaction, this is 20. Okay. So in this cross section, this is 20, and this cross section, basically this cross section respect to this portion is the same, but there's an action reaction. So here you are doing the right, okay? And so if you would take the cross section on the top here, if you would take the free body diagram of the upper portion, then this is the reaction should be like this. If you take the free body diagram of the middle portion, then the reaction should be like this. Okay, that basically is the concept of the action reactions. Okay, but anyhow, we have determined the magnitude, and we still able to determine the cross-sectional area. Okay, divide the force by cross-sectional area, again magnitude, the unit. Then again you can that together with the direction of the shear stress, and you can determine, uniquely define the shear stress. And again, if you pick this free body diagram, then the shear stress must be in that direction. If you pick this as a free body diagram, then the shear stress must be in that direction. Okay, really depends on which way you pick to illustrate the shear stress. Everything is consistent. Okay, again, everything is consistent So now we come to our another term called the bearing stress. And again, the bearing stress is very kind of very rough, uncommon definitions, and this term only appeared in chapter 1. Again, this term only appeared in chapter 1. The bearing stress is this. We sometimes people interested in knowing want to calculate the distribution of the stress along a curve, along the curved surface. Okay, just like here. Okay, that is a hole we drill to accommodate to house the pin. And so determinations of the stress along a curved surface is very involved. But for the beginners, we can make a very rough estimation. Basically, the way is this: if you project the curved surface to this onto this area, okay, so basically you can very roughly approximate this distribution of the stress on the curve by using the distribution of the stress on this projected area. So P divided by A, this projected area simply equal to T times D. Okay, and in this case, this one we call the bearing stress. And again, bearing stress is a very rough approximation of the stress on the curved surface to a projected area we call the bearing. Okay, again, this term is very rough, only appear in chapter 1. So this is a very quick calculation application of the bearing stress around the pin, around the hole that housing the pin A here. So 40 divided by TD, and you can figure out this is the D, and the size is T. Okay, so basically that is a quick calculation here.